Okay, so we'll wait for 5 more minutes and let's see if anyone joins. Then we'll start. Okay, so let's begin. I hope I am audible and you can see the screen. So just to make sure you are joining the right course or the right session, this is NOC EE-62, NPTEL tutorial on basic electronics. The course is being offered by IIT Bombay Professor Mahesh Patel, and I am a tutor for this course, Debashish Nandi. I am from IIT Kanpur. As you know, this is a 12 weeks course, and this tutorial session is scheduled every Sunday 3 to 5, right? So there are some prerequisites, as I am reiterating this, as every week I do the same, that you are expected to attend the previous week lectures and be thorough with it so that you can follow this lecture, this problem solving session thoroughly. And also it is expected to the attendees that you have at least attempted the previous assignment posted, right? Then it will help you to solve the purpose. And I will request you to follow certain decorum, that be muted all the time. If you have any query, you can use the raise hand option, or you can unmute. That will also work. And also after each problem or topic I discuss, I will give you some time to ask your doubts. And at the end of the 2 hour, as it is a 2 hour session, I will be assigning 10 minutes of time for you to ask me general questions or query regarding this session. Please make sure that you are having a scientific calculator with you during the session. It will help you to do the problem simultaneously. Okay, so let's begin. This is week 5. Today is 5th March. So today we'll be basically discussing BJT common emitter amplifier configuration. Okay, so let's move on to the first problem. So let's make it more larger. Okay. So it is mentioned that, yeah, can anyone confirm that am I audible? Or you can...
Yes, sir.
Yeah, fine, thank you. So moving on to the first problem, it is mentioned that, as usual, for NP and BJT transistors, bipolar junction transistors, you need to consider BBE, base emitter junction, as 0.7 volt. As you know, it is a PN junction, right? So to be it in the active mode, or the base emitter junction is needed to be forward biased. This was discussed in the last session, and it should be 0.7 volt. And for saturation, the VCE output or collector emitter voltage should be taken as 0.2 volt in the saturation region and in the active region, right? So similarly, not in the active region, in the saturation, the boundary of the saturation and active region. Also, for the PNP transistor, you just reverse the polarities of the contacts, right? So your VBE will become VEB. So this is general stuff. And your thermal voltage is taken as to be 26 millivolt. Last session, I have discussed how it is coming about and how you can calculate it for any temperature, right? Also, assume beta to be very large unless it is specified. But beta is very large means your alpha is almost equal to 1, right? So let us move on to the first problem. So a common emitter amplifier shown is given, and it is mentioned that the BJT is operating in active mode, right? Why do BJT needs to be operating in active mode? Because we are using it as an amplifying operation, right? If you have gone through the lectures, you will be aware about this, that why for amplification applications, we need the transistor to be in forward active mode. So they have asked us to find out what is IC. That means we need to find out the DC collector current. So how to go about this? See, you can see that the circuit is very large, right? There are capacitances and all. So for DC bias conditions, your frequency F or omega is 0, right? That means your XC is 1 over J omega C. Whatever the value of capacitance is, it will be simply infinite, right? That means we will treat this as an open circuit. Hence, you can ignore this. So how will your circuit look like? DC equivalent will be looking like this. You have your transistor, you have your emitter resistance, you have your collector resistance, and you have this kind of biasing network, right? Can anyone tell me what kind of biasing is this? What is the name for this kind of biasing? You can unmute yourself and tell me. Anyone? Okay, no issue. This is called a voltage divider bias, right? The name is voltage divider bias. And the reason for the name is simple, because you do not apply a additional base voltage at this point. You just simply use the same collector voltage and use a voltage division network to get your proper base voltage, right? So how do we analyze this circuit? The way to analyze this circuit is consider this portion of your network as an input side and this portion as output side. This you consider as input side, this you consider as output side. What do I mean by that? Let's call this load. In general terminology, these are right. So this is your load or output side. This, what do you have? You have voltage source and some resistance, right? This is resistance, and this is common to this side also. So this is a voltage source. So how do you simplify this? This network, you are well aware that this can be Thevenized, and you can simply this is your load, right? I think this is clear to you that this can be treated as a two-port network, and we can find out the equivalent Thevenin voltage and resistance. So how do I find out the equivalent Thevenin voltage? Thevenin voltage is nothing but open circuited voltage at this terminal, right? So from this, you can see if I open circuit the load, that means this circuit becomes, this is your 12 volt, this is your 20K, and this is your 15K. And from this point onwards, this is load. So if I open circuit this, so I remove the load, and I need to find out the potential at this terminal, right? VTH. So your VTH becomes 12. It is nothing but a voltage divider. 15 over 20 plus 15. That is nothing but 12 into 3 by 7, that is 6 by 7, is nothing but 5.1 volt. Okay. So how will you calculate this equivalent RTH or Thevenin resistance? The method is simple, as you already know, that to calculate this, we need to null all the independent sources and find out resistance looking into the terminal. Okay, so the way to do is you null this source, right? That means your equivalent circuit becomes, this is your short circuit, and there you have another resistance, and this is your terminal. So you see from here, right? This is your RTH. This is your 15. This is your 20. So your RTH is nothing but parallel combination of 15 and 20K. And it is nothing but 3. This is 7. So this comes out to be 60 over 7, 8.5K. Okay, so you can simplify this diagram as follows. So your circuit will look like now. This is a 12 volt. This is not given. This is 3.3 kilo ohm, and this is 8.5K, and this is your 5.1 volt, right? This I think you have done in your last week, right? This is a fixed bias circuit, right? And you know how to analyze this circuit in active mode. The way to analyze this circuit in active mode is you consider this voltage drop across. This is base, this is collector, this is emitter, this is to be forward bias, so we assume it to be 0.7 volts, right? This current is your IB, this current is your IC, okay, and your beta is given to be 120. So if you analyze this circuit, just follow this loop. So if you write KVL in the input loop, KVL in the input loop. By the way, this is called in common configuration, this is called the input loop and this is called the output loop, right? So your 5.1 minus IB times 8.5 minus 0.7 minus I. This is your IC, this is your IE, and IC is almost equal to IE because my beta is much larger than 1, right? So you can simply take this as IB into beta 120 into 3.3 is equal to 0. So this becomes 4.4 is equal to IB into 8.5 plus this is your 120 into 3.3 is your 396. So your IB becomes 8.5 plus 396, 4.4 answer is around 1.087 into 10 raised to minus 2 milliampere, right? So that means this comes out to be, do I have any option? This is IB, right? We were needed to find out IC. So your IC would be nothing beta IB 1.087 into 10 raised to minus 2 milliampere, and this 2120 is 1.3053 milliampere. Let's see if we have any option. 1.3, yeah. So your B will be the right option, right? This is pretty straightforward. So if you have any question, I would request Gauri M. Chavan to please mute yourself if you do not have any question. Okay, so let's move on to the next problem. This is the same circuit is given. They want us to find out the value of RC is when my VCE is 5 volt, right? So let me just copy this equivalent circuit because my input side is not changing. Input side remains same. So for DC analysis, I can simply have this just so they want us to find out what is RC when my VCE is 5 volt, right? So given the current input bias condition, I know my IB and IC, right? IB and IC are known. So my IC is nothing but it has come out to be 1.3 milliampere, right? Now I will focus on the outer loop. So what do I have? I have nothing but 12 minus IC. This is my IC. This is my IE. So IC into RC minus 5 minus IE can be taken almost equal to IC into 3.3 is 0. So your 7 is nothing but IC into 3.3 plus RC. So my RC is coming out to be 7 divided by IC is 1.3 minus 3.3. So 7 divided by 1.3 minus 3.3. 3.3 is coming out to be 2.08 kilo ohm. Okay, so do I have an option? Okay, let's go with this. We can also go with this, but this is more closer. So let's go with 2K, right? So 2K is my right option. This is pretty simple. So let us remember this value. This we will require to solve the next problems. So moving on to problem number 3. With RC set to the value obtained in Q2, what is GM? Right? They want us to find out GM. So what is the definition of GM? What is GM actually? Anyone? Can you unmute and tell me? Let's make this interactive. It doesn't matter whether you know it or do not know. It will help you eventually. You can unmute and tell me what is GM. Not the formula, the actual meaning, what GM is. Gautam, Gauri, anyone?
Yes, sir. Sir,
Please go
conductance.
on. What do you mean by conductance?
Sir, I have no idea.
No. See, you are in the
One
right track,
upon
right?
resistance.
Yes, right. Suppose I am having a resistance here, right? So this is my R. This the current is flowing in this terminal, right? And this is my V, let's say. So my conductance, let's say, Y is 1 upon R is equal to I by V, right? This is what you are meaning to say. Can you please mute yourself, Gauri?
Yes, sir.
Can you please mute yourself? Yes, thank you. Gautam, please unmute yourself and tell me why this is what you meant.
Yes, sir.
So, right, this is conductance, right? But GM is generally called transconductance. Have you came across this term? Have you come across this term earlier? Transconductance. Transconductance means, suppose you have voltage. Suppose you have this kind of scenario, right? There is a potential drop across this. Say this is your V. Let's say this is your V. And this is your I, right? Now the symbol is of a controlled current source, right? So now if it is a voltage controlled current source, that means if I is some alpha, let's not say some alpha, some GM into V, then I equals to GM into V means voltage across, current across this terminal is dependent on voltage across some another terminal, right? In this case, what is happening? In the same terminal, you are having the voltage applied and the current is flowing, right? This is called conductance. And transfer conductance or transconductance is when current flowing across any branch is controlled by potential difference across any other branch. That is how the term transconductance has come across. So GM is generally transconductance. Now for a BJT, transconductance is defined by delta of IC with respect to delta of VBE. Okay, that means this potential drop, if I change this potential drop by a differential amount, how much my collector current is changing? Note that this collector current is flowing between these two terminals, and this current flow is being controlled by another two terminal, right? This is the fundamental behind any amplification operation. So this is called transconductance. For this case, del IC by del VBE. Last week I have shown you how we found this expression. Exponential VBE by VT, where VT is your thermal voltage. Right? So what is the logic behind this expression? Is nothing but your IC is some proportional to IB, right? It is equal to beta IB. Beta is, if I take beta is constant and independent of IC, then IC is proportional to IB. And IB is nothing but the current flowing in a PN junction. Okay. So PN junction, we know that ID is nothing but I naught e to the power VD by VT minus 1. Similarly, in the same manner, we get this expression. Okay. So if you have this expression, I think it is pretty straightforward to calculate. It is pretty straightforward to calculate this DIC by dVBE, that is d of dVBE of this expression is e to the power VBE by VT. So it is is e to the power VBE by VT into 1 by VT. That is your, this is nothing but your IC divided by VT. So what was your IC for this same configuration? Your IC was 1.3 milliampere, right? So your IC was 1.3 milliampere divided by your VT is at room temperature 26 millivolt, right? So 0.026 volt. Ampere by volt is Siemens. So 1.3 divided by 0.026 millisiemens. That is nothing but 50 millisiemens. Okay. So yeah, A is your right answer. This is how you go about to solve this kind of problem. So moving on to the next problem. Okay, with RC set to the value obtained in question number 2, what is R pi? Okay, now you need to understand the small signal model, right? Okay, let me tell you in an interesting way. You might have seen this equivalent circuit, right? This is your GM VBE. This is your B. This is your C. This is your E. This is R pi, and this is your VBE. Can any one of you tell me how this circuit has come about? What is the starting point? Anyone? Just guess. Take a wild guess. Gautam or Gauri, take a wild guess and just let us develop this circuit. It is very simple and very trivial, but it will be very intuitive for you to analyze circuits in future, how to go about modeling this with some known elements, right? We know resistance, we know control source, but how do we get this? Anyone can unmute and comment. It does not matter whether you are right or wrong. Just take a wild guess. Okay, no issue. Let me go about it. See, how do we model things, right? First, let me, if I ask you to plot IC versus VCE, how will the plot look like? You all will, I am pretty sure that you all will be absolutely right in plotting this. And this you will say IE or IB increasing. Okay. Now, this model you need to understand is valid for forward active region. Okay. So forward active region, what is my forward active region in this plot? If I segregate this plot, let's say like this, actually it is somewhat like this. Let's say this is my forward active region, right? This is my forward active region. Now tell me, how do I model So if I just curtail the curve, if I just curtail the curve like this is an IV plot, right? Simply we have a straight line. From this plot, can you guess what is the element across which I am measuring I and V? My question is, if this is a network element, this is my I and this is my V across it. What is this element? It's a current source, right? Current source doesn't concern about what is the voltage across it. It provides a constant current, right? So I know that this element is a current source. Either this or it is a control current source, right? How do I know which one it is? If any of the current and voltage parameter, if I vary, if any of the other current voltage or current parameter or current values, do my this level shifts upward or downwards? That I need to check, right? Now, tell me, if I have this kind of plot, and this I say is a IB, let's say. If IB is increasing, this plot is moving up, but it is maintaining the horizontal line, right? Then what does it mean? That for a particular voltage, if I change my IB, then let's term this for a particular VCE, if I change my IB, then my IC changes. That means it is a controlled source. The controlled element is IC and the controlling element is IB. That means it is a current control current source. So I will go with this guy. Okay. So I get this. This is, let's say, my beta or into IB. Let's say this is my beta into IB. Okay. That means somehow I need to have a current IB. So this is my C. This is my E. Let's say somewhere I need to have a current IB, which controls this current. Now let's say, what is my IB? Now IB needs to be flowing from my base to the, if you see, this is my IB, right? This is my IC. I am trying to model this thing, this enclosed guy, like in a small signal sense. Okay. So this is my IB. Let's see, for the time being, this is grounded and emitter is also grounded. Okay. So this is pretty fine. But do I have a short circuit here? Short circuit means my VBE is always 0, but I cannot sustain that. My VBE has to be having some value. That means I need to have a voltage drop across this. So I need to have a resistance. So let us call this resistance as R pi. Okay. So this is how I model this section. Okay. Or let me use this. So this is modeled here. Now tell me, do I have a straight line? Do I have a straight line in this plot? I do not, right? I have a particular slope. That means if I draw my IV, it has slopes like this, right? It is not, it has certain slope. The slope is not zero. How to take care of this? What does that mean actually? That means my VCE and IC, across it there is certain resistance, right? One thing is that I change VCE as it is and my current is constant for a particular value of VB, particular value of IB. But now I have, apart from a current source, I have a dependence on the output, dependence between output voltage and collector current. That I can model by simply having a output resistance. This is your R pi, this is B, this is your E, this is C, this is GM-VBE, or you can say IB into beta, this is your VBE. Okay, you note that your IB is nothing but VBE by R pi, right? And your GM-VBE is not, it's equal to your this IB into beta. Okay, so if you substitute VBE here, GM into IB into R pi is equal to IB into beta. IB cancel, then your R pi becomes beta by GM. Beta by GM. Okay. So I think you understood how this guy came about. This is coming from the fact that you have a slope. This slope is referring to your output resistance. And if you have gone through the lectures, you would have seen that all these lines meet at the negative in a negative VCE axis at a certain point. That point we call VA or early voltage. Okay. So this is how the small signal comes about. So this is a very trivial way to model anything, right? You know certain network elements. You know the characteristics. These IB characteristics, you know the output characteristics. Now you need to find out regional analysis. In the forward active region, what will you see? You will see how my curve is looking like and what are its dependencies. So you see, first we have found out that it is a straight line. So it should be a current source. Now the next question is whether it should be a control source or a independent source, independent current source. You see that your IB controls this. So it is a current control current source, right? So you need to have some IB flowing in the circuit. Then you find out that how my IB will be flowing between base and emitter. There has to be certain potential drop because to be it in a forward active region, you need to have 0.7 volt. So we have certain resistance there that is called R pi. And pi, why it is called pi? Because if you invert this, it looks like a symbol of pi, right? Then what happens? You see that your lines are not with a zero slope, right? It has certain slope. To encounter that slope, you need to find out how a slope in IV relation can be taken care of. That can be taken care of by simply putting a resistance, right? So that is how the small signal circuits have come about. Okay. So I think now you can take any random curve, start with straight lines of IV and you try to make the small signal circuits. That will be a very good exercise for you. And these things, these sub-circuits are actually very helpful in the device modeling if you are interested in pursuing that career future, that in future, that will be very helpful. Okay, so you know how to find RPI. So your question is now, this is, what is RPI is your question, right? So RPI, you know, is nothing but beta over GM. Beta over GM. Beta, you know, is 120. What is GM? GM, you have find out 50 millisiemens. So this would be nothing but 2.4 kilo ohm, right? So B would be your right option. Okay. So let's move on to the next problem. So problem number 5. With RC set to the value obtained in Q2, suppose R2 is varied. So this is not given. Suppose your R2 is varied. Okay. At what value of R2 approximately will the BJT enter into the saturation? Okay. So we'll start with its DC equivalent. Before starting that, why I am doing DC analysis, right? DC analysis is being done here because I assume this VS to be very small compared to my applied bias. Okay, so it cannot shift my operating point or the question point. If my VS is comparatively higher, then my analysis will change. And I cannot only simply use the DC analysis. I have to consider my VS also. Okay. This is particularly important in the boundary regions of active, forward active and saturation, also forward active or cutoff, right? So this circuit is 12 volt, RC set to the value, it was 2K. Then this was my 3.3K. This was, okay. This I cannot do because R2 is not given. Okay, so this is 20K and this is my R2. So I can do like 12 volt, 2K, 3.3K. This is RTH, this is VTH. So my VTH would be 12 into R2 by 20 plus R2. R2 is in kilo ohms. So 12 R2 by 20 plus R2. And my RTH would be parallel combination of these two, right? So 20 R2 divided by 20 plus R2. Okay. So now for saturation boundary, we know this to be 0.2 volt. That means my 12, this is KVL at outer loop. Minus IC into 2 minus 0.2 minus, let me take IC and IE same. This is my IC, this is my IB, right? So this becomes IC into 3.3 is equal to 0. So my IC would be 11.8 divided by 5.3 milliampere. and it is coming out about 11.8 divided by 5.3 is 2.226 milliampere. So my IB would be 2.226 by 120 milliampere divided by 120 is 0.0185 milliampere. Okay. So I know IB. Now I need to find out R2, right? So now if I apply KVL at this loop, we see that your VTH minus IB into RTH minus 0.7 volt minus IC into 3.3 is equal to 0. Your VTH was 12 R2 by 20 plus R2 minus 20 R2 by 20 plus R2 into your IB. Let's put it IB for the time being. 0.7 minus 120 into 3.3 into your IB, right? So if I just do that, it becomes 12 R2 minus 20 R2 into IB minus this comes out to be 20 into 0.7 is 14 minus 0.7 R2 minus this is coming out to be 120 into 3.3, 396. Let's take it 400. Let's keep it 396. It doesn't matter. 396 IB into 20 plus R2 is equal to 0. Right? So your R2, if I take common, then 12 minus 20 into IB is 20 into 0.0185 is 0.37 minus 0.7 minus this 396 into I2 is 396 into 0.0185. That is 7.326 is equal to 14 plus 396 into 20 into 0.015. So 396 into 20 into 0.015 plus 20 is 166. And your R2, this becomes 12 minus 0.37 minus 0.7 minus 7.326 is 3.604. That means your R2 is coming out to be 3.604 is your 46.2 kilo. So do I have any option for this? Yes, I think 45. Say it is approximately 45. Okay. Any doubt regarding this? As you are not interacting, so I am assuming that either you are getting the every insight of this course, or if you are not getting anything. So I will assume that you are getting everything. Again, I will request you, if you have any
Yes.
doubt, you can unmute and ask, right? Anytime. Okay. So let's move on to the next problem. This is asked that what is the value obtained Q2? What is the mid-band gain magnitude of this? Okay. So it is asked to find out the gain, okay, in the mid band. What do I mean by mid band? First thing, if you see the gain versus frequency plot, let's say this is frequency, let's say this is gain. You would see this kind of characteristics, right? So this looks like a bandpass filter, right? Your gain is high at some certain frequency range. Let's say this is FL, FH. In between there, you have a constant gain, and then your gain drops at high frequency and in low frequency, right? I will just mention this much. You can refer to the lectures because I will not have will be having time to explain this in detail. This lower limit is basically controlled by your CC, CE, and CB. Okay, and this limit is controlled by, or the higher cutoff is controlled by your C mu and C pi. Okay, what are these? These are nothing but the junction capacitances. Okay, and in the mid region, capacitances do not play any role. Okay. Can you tell me how can I say that in the mid region capacitances do not play any role from this plot? Anyone, please unmute yourself, and it is very interesting actually. These are some basic concepts which I am poking you every time to see whether you know it or not, whether you are
Because it
getting the
is
essence.
constant.
So
Constant.
yes, right, you are right that it is constant. So I can say that capacitance does not play any role, but how? Yeah, can you comment on that? Why a constant anything is, if from frequency, if I sweep frequency, right? This means if I sweep my frequency, I have a constant gain. Yes, I think you are right. So this means that if you sweep your frequency, there is no element in your circuit which is responding with respect to your frequency. Now in your circuit you have controlled current sources, you have controlled sources, you have independent sources, you have resistances. These all are frequency independent elements, right? Now if you have in your circuit, if you have capacitances or inductances, then only you have a frequency varying response, right? So as you have rightly said that as it is constant, so no capacitive action is being effectively played in this region, right? So if that is the case, then it is asked us to find out the mid-band gain. Okay, so if I draw the equivalent circuit, what will it look like? You have a capacitance, then you have a resistance. This is effective resistance R1 parallel R2. Then you have a base resistance. You have this, and you have another path to this. And then you have your RC. Okay. Then you have this. And your this is CC. This is CB. This is CE. This is your E. This is RC. This is RL. Okay. And now you have V0 by VL. Okay. So you have this R pi. Okay. This is your GM, VBE. This is your B, this is C, this is E, and this is your VBE. Okay. So how do you calculate your gain? Your V0 is nothing but, now let's say your frequency range is such that your capacitances are acting as a short. Okay. When will that happen? Again, J omega C, if your omega C is omega C is much higher, then your XC is almost zero. That means impedance spacing is almost negligible, right? Then you can simply short this. Okay. If you short this, this will go away because it is having another shorted path. These two will be coming into parallel. This is your B0, right? So, what is the current flowing this way? This is your IC, is nothing but your, your IC is nothing but GM into VBE, right? And what is your VBE? Can you see that your VBE is nothing but your VS? Because this node, and this node are same, right? This is grounded through this. This is grounded through this. This is grounded, this is grounded. So this voltage is nothing but this voltage. Okay. VBE is nothing but your VBE is nothing but your VS. And what about your VO? Your VO is nothing but total this impedance RC parallel RL IC into minus IC into RC parallel RL. Why it is minus? Because current is flowing out of the resistance, right? Because a current is flowing out of this contraption. If it is going in, then your V0 will be positive. This is passive sign convention. So your IC is nothing but your GM into DS parallel to RC parallel RL. Okay. So this becomes your minus GM into VS. Now they have mentioned if RL is large. How large? Let me take RL to be infinity. Okay, that means this is an open circuit. I can simply ignore this. Then my RC parallel RL becomes RC only. That means this into RC. That means my V naught by Vs is minus Gm into RC. Now the question RC, I know RC is nothing but 2K. In Q2 we have found out it is to be 2K. And Gm I know is to be, what was Gm? Gm was 50 millisiemens, right? So my Gm is 50, 10 raised to minus 3 into my RC. RC is nothing but 2.22 actually 2 kilo ohm, right? This goes away, this becomes minus 100. So they want us to find out the magnitude, right? That means mod V naught by Vs would be nothing but equal to 100. So D is your right option. I will request you to please go through this part, why this and this are limiting your frequency response and how this come into play, right? If time permits, I will discuss this today or probably next week. This is basically due to the devices. This is basically due to the device's intrinsic capacitances. These are very small. These are called basically parasitic capacitances. So if parasitic capacitance, how do you remember that? Which this is very interesting. How do you remember that these capacitances are limiting, the external capacitances are limiting the lower limit and the internal capacitances are limiting the upper limit? The way to remember is that is this formula, right? For a certain frequency, if my capacitance is very small, right? For my capacitance is very small, then at higher frequency, I will have similar kind of impedances, right? So if C is small, to keep my XC constant, I need to have higher frequency. Like these capacitances, internal parasitic capacitances are generally very small. So this generally takes limits your gain at the higher frequencies. This way you can remember, and the other way, and vice versa for the this CC, CE, and CB. These are called coupling capacitances. Okay, let's move on to next problem. Okay, this is with RC set to the value obtained in Q2. What is the mid-band gain if RL is 2K? I think this is pretty simple. We have already found out the expression that this is to be minus Gm into RC parallel RL. Now Gm is 50 millisiemens into this is 2 kilo ohm parallel 2 kilo ohm. So this would be minus 50 millisiemens into 1 kilo ohm. So this is nothing but minus 50. So magnitude of this becomes your 50, right? So you see, if you're in, you can see that what does the RL, how does the RL is affecting here? If your RL is less than infinity or your load resistance is not infinite, so your gain of the amplifier reduces, right? Did you get that? Suppose your output impedance, your input impedance of your next stage or your load is infinite, which is the case for a MOSFET. Say I have a MOSFET, input impedance is almost infinity, right? So my RL, and this is my, say, this is say your amplifier, common source amplifier, and you are connecting it like this with a coupling capacitor. If this is your infinity, then my gain of this stage is better, right? So it is always it is always taken into consideration whether the input impedance of my amplifier is how much, whether it is infinite or not. This is one of the reasons why MOSFET is preferred over BJT. You know, one is your that CMOS thing, that is your static power dissipation is almost negligible in your CMOS circuits. Another thing is this, that your input impedance is infinite in case of MOSFET, right? Because I cannot have, suppose I need to amplify a signal 1,000 times. I cannot have 1,000 gain amplifier. It is preferred that I have, there are certain certain trade-offs, with gain and bandwidth and certain things. So I have to have multi-stage amplifiers. So I need to have my input impedance of the next stage of amplifier is as high as possible. So the correct answer would be here 50. So moving on to the next problem. With RC set to the value of T, what is the output resistance of the amplifier? Okay. As seen from RL means what is my output impedance looking here. So if I have this circuit, let's copy this circuit. So this is my RE, this is my CE, this is my RL. Right, this is my CC. Again, I will assume that my capacitances are such that the omega C is much higher and my equivalent circuit looks like this. And this is also shorted. This is sorted. And this becomes my overall circuit diagram, and I need to find out the output impedance looking from this side. Okay, this is R out. You notice that R small r not due to your VA by IC or your early voltage. We are assuming it to be infinity, right? Please note this. So I do not have any additional R naught here. Okay. So to calculate output impedance is nothing but, it is a very trivial task. It is nothing but similar to calculating your Thevenin voltage, Thevenin resistance, right? So how did you calculate your Thevenin resistance? You have calculated your Thevenin resistance by making sure that your all the independent sources are null, right? So this is my independent source. Let us null this. That means it is shorted. That means it is 0 volt. If Vs is 0, my VBE is 0 volt. If VBE is 0, then my this fellow is 0 ampere. If this is 0 ampere, current source 0 means it is open circuit. So my equivalent circuit becomes nothing but this, and I need to find out resistance R out. So what is my R out? R out is nothing but RC here, right? And your RC is nothing but 2 kilo ohm. That means your B is right option. Again, I will explain. First thing is to do, you think that output impedance is nothing but calculating the Thevenin resistance, right? To do that, you need to ground the source, or you need to null the independent sources. This you have nulled means this you have short circuited. Then next step, you see that what is the effect of nulling this source. You see that your Vs was equal to VBE, because as I mentioned, these terminals and these terminals are same. So potential across this will also be same. So my VBE will be 0. If my VBE is 0, that means my this current is also 0, because it is a controlled source, GM VBE. If current source is 0, that means it is an open circuit. If it is an open circuit, then my circuit diagram looks like this, and it is very simple to see that my R out looking from RL is RC, and RC is 2K. I think it is clear. So moving on to next problem, problem number 10. With RC set to the value obtained in this, what is the input resistance of the amplifier? So how do you calculate input resistance? Again, let me copy this circuit. You can simply so this becomes this, grounded, this becomes RL. Okay. So what is your input resistance, right? Input resistance, or finding out resistance between any terminal. One way is, as I have told you, that Thevenin method. Another way is you simply apply, suppose this is a network and you are asked to find out the input resistance. Simple method is you apply a V test here, test voltage. You calculate I test and you take the ratio. R in would be your V test by I test. Okay. As simple as that. So in this case, let us say my Vs is V test and this current is my I test, right? Now what is this current? If I see that, if I see this part of the network, right? This current is going through this and this. So I can simply make a parallel combination of this. So my equivalent circuit will become V test and a resistance which is R1 parallel R2 parallel R pi, right? This current is flowing through this, right? Why it is not flowing through the here? Here it will see certain impedance, right? It has two paths. One is directly grounded, another path it is seeing certain any non-zero impedance. The entire current will flow through the short circuited path, right? So this is your I test. So as you can see here, this R in will be nothing but R1 parallel R2 parallel R pi, R1 parallel R2. We know it is 8.5 kilo ohm, and your R pi is nothing but, what was your R pi? Your R pi was 2.4 kilo ohm. Your 2.4 kilo ohm. So 8.5 into 2.4 by 0.5 plus 2.4. That is 8.5 into 2.4 divided by 8.5 plus 2.4 is 1.87. Okay. And do you have any option regarding that? Yeah, this 1.9. Let's take it. 1.9 kilo. Okay. So see from one circuit how many things you can analyze. We have discussed almost 10 questions from one circuit. So what I suggest you that you take from any book, Cedra Smith or Boylston Nesselski or Millman Halkias, any book, you take out any circuit and try to analyze everything. First analyze the DC biasing conditions and see whether I am in saturation, whether I am in active, when I am in active, when I am in saturation, when I am in cutoff. Then you move on to the AC analysis, see the gains, see how the capacitances are playing, and limiting the frequencies, right? You do it for 2 or 3 circuits, and let me tell you, you will be very good at this circuit analysis. Okay. So let's move on to the next problem. Okay, this is a new question. The T model is an alternative small signal model of a BJT, and it is shown in the figure. Fine. Along with the hybrid pi model. Okay. I have forgotten to mention that this model is known as hybrid pi model, whatever we have been discussing, right? And it is not a complete model, as I have told you that there will be a resistance here if you consider the early effect into consideration. So these two are equivalent, different way to represent, right? So they have asked us the parameters of the hybrid pi models of a specific BJT operating under some specific bias condition are given by R pi. R pi is given to be 2 kilo ohm. GM is given to be 50 millisiemens. We know what? You remember the relation we have found out between beta, GM, and R pi. Let me show you. Did we find out the relation? Right? Here is the relation. R pi is nothing but your beta over GM. So your beta is nothing but GM into R pi. Also keep in mind to cross-check the dimensional analysis to perform the dimensional analysis every step. Right? See, this is a conductance, this is a resistance. So the product of them will be a unitless quantity, as beta is a unitless quantity, right? So it is matching it is dimensionally consistent. So this becomes your 2 into 50 is equal to 100, right? Because milli and kilo will get cancelled. So your beta is 100. Now they want us to find out what is alpha. Alpha is nothing but beta over beta plus 1. That is 100 over 101. And if you calculate, it will come out to be 0.990. Okay. So C is your right option. You know that your IC is nothing but beta IB. Your IE is IC plus IB, and your IC is equal to alpha IE. You substitute this here, you get the relation between beta and alpha. And you use this. This is pretty simple. So moving on to the next problem. Again, this is in the T model of question number 11. What is RE? RE or RI? Then what is RE? Okay. So you need to find out, this is your RE, right? So this is your EBE. This is your EBE, right? So in this case, from hybrid pi model, VBE is nothing but IB into R pi. And from P model, PBE is nothing but IE into RE, right? So your IB into R pi is equal to IE into RE because both models are equivalent, right? So your RE would be R pi into IB over IE. That is R pi into let's take, we can assume it that IE equal to almost equal to IC. That means IB by IC. That means R pi by beta. Your R pi was 2 kilo ohm and your beta was 100. So it was to be 2000 by 100 ohms, it is 20, right? 20 ohms. Approximately, you can find it quickly, or if you can simply substitute IE as IC plus IB, then you can get it exactly 19.8. Okay. So this is problem number 12. Let us move on to problem number 13. Okay, a push-pull amplifier configuration is shown in the figure. The transistor beta values, beta is 150, here beta is 80. With Vi 2 volt, what is I1? Okay, hint is given. Note that only one of the transistor can conduct. Okay, let me ask you this question. Why does the hint holds true? Hold true. Why? How can we say that only one transistor can conduct at a time? Can you please unmute and tell me? Anyone? Gauri or Gautam? Anyone? Am I audible? I think I am. Maybe by some. Okay, let me explain this. How the hint is holding true here, right? You have an NPN transistor then our PNP transistor minus 5 volt. This is 5 volt. The bases of those are connected. This is VI. This is 5 kilo ohm. And you have here your 2 kilo ohm, right? Okay. This is your I1. This is your I2. The question is, for the, okay, just let me do one more thing. This is N, this is P, this is N, this is P, this is N, this is P, right? I told in my last session that how these diagrams have come about and how to remember these things, okay? So I'll suggest if you have any confusion, you can go back and check that. So the first thing is for, let me tell this name, this is Q1, this is Q2. So Q1 will be on when VBE is greater than equal to 0.7 volt, right? That means this is B, this is C, this is E. This is E, this is B, this is C. This voltage, say this is A, and let's say this is B. VBE is 0.7 volt. That means VAB should be greater than equal to 0.7 volt. Similarly, Q2 will be on when VEB Q2 is greater than equal to 0.7 volt. That means VBA this is 0.7 volt. VBA greater than equal to 0.7 volt or VAB less than equal to 0.7 volt. So can you make sure that these two conditions are simultaneously valid? Can these two conditions be simultaneously valid? This cannot, right? Because it is just making sure that you can think it this way, that your battery is connected and you just reverse the polarity, right? At the same time, you cannot make the between two terminals 3 volt and minus 3 volt at the same time, right? So that's why you will be having one transistor on at a time, another transistor in a cutoff mode at the same time, right? That's what it is meant by that. Note that only one transistor can conduct. Okay. So now the push-pull amplifier configuration on this, the transistor beta varies from this respectively. It is if Vi is 2 volt. Now see if your if you see your Vi, let me copy this circuit. Just see that if your Vi is 2 volt, right? So Vi is 2 volt. And what is the possibility of which transistor to be on? This is positive voltage, right? Current is flowing in this way. So possible case Q1 is on. And from our earlier analysis, we can conclude that if Q1 is on, Q2 is off. Okay. Then my circuit diagram will become simply this. Okay. It is simply a normal fixed biasing method, right? With RC is 0. Then what did they ask us? They asked us what is I1. They want us to find out this current, right? They want us to find out what is I1. So how can I find out I1? It is simple. The 2 minus your I1 into 5 kilo ohm minus, now it is on, so it will be 0.7. So 0.7 minus I2 into 2 kilo ohm is equal to 0. And I2 is nothing but my emitter current, which is nothing but my collector current, which is nothing but my beta into I2, beta into I1 or IB. IB is equal to beta into I1, and beta is my 150, right? 150 into I1. So 1.3 is equal to I1 5 plus 150 into 2. So my I1 is nothing but 1.3 divided by 305 milliampere. So 1.3 divided by 305 is 4.26 into 10 raised to minus 3 milliampere, 4.26 microampere, right? Do I have an option? Yes. Your D is your right option. Okay. So moving on to the next one. For the push-pull amplifier with Vi is equal to 2 volt, what is I2? So again, if I copy this circuit, I have found out IB equal to I1 equal to 4.2 microampere. So my I2 or IE would be IB into beta plus 1, or you can simply take it beta times IB, IC into 4.2 microampere. That, sorry, IB into beta plus 1. So IB is equal to 4.2 into 10 raised to minus 6 into beta plus 1 would be 151 amperes. That is 6. This would be your 6.43 into 10 raised to minus 4 ampere equal to 0.64. Okay, so your answer would be D. Right? This is very simple problem, but the trick was the hint, right? Suppose the hint was not given, then you should have just do this part. Okay. In most of the cases in future, you will see that these hints will not be given. So then you have to apply logic and find out how to go about this. Similarly, problem number 15. Problem number 15. If I same problem, but here now VI is mentioned to be minus 2.5 volt, and as this is in a more negative way, in a more negative voltage will be applying at this base terminal of both Q1 and Q2. So for possible case, my Q1 will be in cutoff and my Q2 will be on. Okay, that means this will be my 0.7 volt. Then how does my circuit look like? My circuit will look like simply this. This is minus 5 volt. This is 0.7. This is VI minus 0.25 volt. This is my I1. This is 5K. This is 2K. Okay. So what is the input loop this time? My input loop is this. Okay. If I analyze this loop, then VI minus I1 into 5K minus 0.7 minus this is your I2 into 2K is equal to 0. VI is your minus 2.5 minus I1 into 5 plus 0.7 minus I2 is your IE is your beta plus 1 IB. Beta is your, where for Q2 your beta was 80. So your beta 81 into IB, right? So it will be 81 into 2 into I1 is 0. Then your I1 would be, this is 162, 167 is equal to minus 1.8. So your I1 would be equal to 1.8 into 0.8 divided by 167 is equal to 1.077 into 10 raised to minus 2 milliampere. Note the sign. So it will be nothing but your 10.77 microampere. Almost minus 11 microampere, right? Nothing in this option. So your D will be your right option. Okay. Again, to do problem number 16, same way, you need to find out I2. How can you find out I2? You need to just copy this circuit. So your I2 is nothing but beta plus 1 into I1. Your beta is 81 into your 11 microampere. Note the sign. So your 81 into 11 is becoming 0.89 milliampere. So the nearest option is D. So option B is correct. Okay. So, okay, that's all I have for today. If you have any questions, you can please ask, or I have still have some time. I may discuss some new topic. Gauri or Gautam, I think you guys are still in the conversation. So if you want to ask any question, you can ask or ask in the chat box, or else I will discuss something new which will be helpful. Let me wait for 2 or 3 minutes if you have any question. Okay, so I think you do not have any questions. So let me go about telling a very important concept which I should have covered in the first session, but due to time constraint, I was saving this for some some lectures if I have some time. So today is the day. Let us discuss this passive sign convention. So what does passive sign convention say? Suppose you have a network element, okay? And this is voltage across it, and this is the current into the element. I into the network element. Very important. And your voltage is across the element. Into the network element in the positive terminal, right? Positive terminal of the voltage across it. Across the element. So what is my power? P is V into I. This is dissipated power. Okay. So this is my passive sign convention. That means I assume a potential drop across an element, and I consider the current to be flowing into the positive terminal of that element, of the potential, right, of that element. So then if my power P is greater than 0, then it is power dissipated. If P less than 0, it is power delivered. Okay. Now, if I draw the IV characteristics of some elements, let's say I draw the IV characteristics of a linear resistor. It will be like this with certain slope 1 by R. If my IV characteristics lies in the first and third quadrant, then power dissipated. Okay. It is power delivered. You will have never a resistance with negative value in conventional sense. So you will always have power dissipated through a resistor, right? Now consider a battery. And current, let's say, flowing inside, right? Let's say this is VB battery. The voltage across it is V. Suppose this is your IV characteristics. How will my IV characteristics look like? First question. My IV characteristics will look like it's a constant voltage, right? That means it's a line, straight line, parallel to y-axis or current axis. It can take any current value. You can see that it is going into two quadrants, right? In this quadrant, it is power dissipating, and if it is in this quadrant, it is power delivering. And mostly my batteries will lie in this and this quadrant. Okay, so you see that this is why it is called an active element, because it delivers power. Its IV characteristics lies in the second or fourth quadrant. Can lie in the second or fourth quadrant. Okay. Now current source, similar current source. Let us do the current source also. Suppose this is I0, this is I, so it is I0. Here you will see second quadrant, so power delivering. Okay. Remember this concept very carefully. Now it's a tricky question, and let me ask you this. What about a diode? This is VT, this is IT, right? This definition, by the way, is valid for a two-terminal device only. Okay. Don't go and ask that why my transistor characteristics is like that and why it is called an active element. That is a different case. How it is giving you the gain in the forward active region, as in case of BJT. Okay. That is a three-terminal device. It is having a transfer resistance characteristics, transconductance, what we discussed in the earlier case. So for a diode, let's say, how will my characteristics look like? IT, VT. This is how my actual diode characteristics look like. So this will be this, and then this, and then this. Okay, this actual diode characteristics, how this is look like. What you are familiar with this. And in the reverse direction, it will have like this, and then so what do you think? Is diode an active element or a passive element? Remember that it has your characteristics only in first and third quadrant. Okay, this is a question I want you to, I will ask it again in the next session. I want you to find out and give me the answer. Okay, this is a homework assignment for you. Another thing, if you see the solar diode curve, right? It has certain portion in the, it's a hint for you to answer this question. It has certain portion in the fourth quadrant. Okay, it does it deliver power only in fourth quadrant? Is it an active device? Is it an active device? Okay, these are some very interesting questions. But rest assured that this passive sign convention you should be following in every circuit analysis for capacitances, inductances, control sources, everything, right? And why my control source is not an active element? Because my control source, my input-output relation will have certain state. It's like a resistive line, right? So you find out this question. Let me write it again. Is diode an active or passive device? Give reason. Solar diode used in solar cells. So by intuition, you can say that it is an active device because it supplies power. But is it so actually? And what about normal PN junction diode? What about tunnel diode? What about Schottky diode? Right? So these things you please go through, and I will request you to go solve the assignment problems very diligently and also follow the lectures. Okay, so we have still 1 minute time. If you have any question, you can ask or we'll end the session.
No, sir.
Yes, please. Okay, you do not have any question. Okay. Just let me scroll through this. If you find anything you want me to discuss again. Or you can simply use that discussion forum, right? In the if the course web page, you will see that ask a question tab. You can simply ask questions there, or you can comment on the YouTube link, which you will be provided. In that, you can simply ask your doubts and we can answer, right? Okay, so let's stop here.
Thank you, sir.